In an earlier video, we took brucite, Mg3OH6, and we wrote it like this, where we have octahedrally coordinated magnesium atoms surrounded by a layer of hydroxyl on top and a layer of hydroxyl atoms on the bottom. Then we took two of those hydroxyls and substituted an Si2O5 unit. Remember the Si2O5 layers will have a charge of 2 minus. So that can be substituted out for 2 hydroxyl units, which would also have a total charge then of 2 minus. So we'd retain charge balance if we make that switch. Well, in the earlier video, we created the minerals lizardite and kaolinite by putting the Si2O5 unit on top. What if we were made to make that switch both top and bottom? So if we did that here, we would have Mg3 with Si2O5 on top, and then an OH over here that's left over, and then an Si2O5 on the bottom, and then another OH here on the bottom. So here we've made the switch both top and bottom, and this gives us, in a more standard notation, Mg3, Si4, we're just adding up the total number of silicon atoms here, O10, we're adding up the total oxygen atoms, and then we have 2 hydroxyls, and this is the mineral talc. We did this by starting out with brucite. If we started out with gibbsite, where instead of 3 magnesiums, we had 2 aluminums, we'd have 2 aluminums here. We'd have a very similar kind of formula, but instead of 3 magnesiums, we'd have 2 aluminums, and the rest is the same, Si4O10, OH2, and this is the mineral pyrophyllite. So here, the only thing we've done differently compared to the prior video is we've added a tetrahedral sheet both top and bottom rather than just to the top. So we have a tetrahedral layer here, signified by these Si2O5 units. We have an octahedral layer. These magnesiums are still in octahedral coordination. And then we have another tetrahedral unit here, as signified again by the Si2O5 units. So these are the TOT silicates. Now, we do have a classification scheme for these. Since all 3 of the octahedral sites that are available here are occupied, then we call this a tri-octahedral mica. And then this fellow over here, it has only 2 of the octahedral sites filled. And so it is a dioctahedral phyllosilicate. Let's look at some other variations on this theme. So we have the TOT layers, and then some weak van der Waals bonds, and then another TOT layer, and then some weak van der Waals bonds. We'll try one more little triplet here, TOT. Well, we can fill in those gaps. So we have these weakly bonded triplets. The bonds between this set of TOT layers here and this triplet of TOT layers here, it's very, very weak. We might be able to pull that apart and put in some H2O. And if we do that, then we would get the mineral vermiculite. So we can write that as Mg3, Si4O10, OH2. So this just looks like talc. Then we're going to draw a dot. Now that dot represents that we're bonding two molecular units. So we have this molecular unit here, the talc unit, and it's going to be bonded to, on average, about 4.5 H2O molecules. That is also molecularly neutral, but there are unsatisfied bonds here. There's some polarity with the H2O molecules, and so together these things can bond and make for relatively weak bonds. That water can easily be pushed out of the structure, collapsing the vermiculite back into talc. But this would be an example of vermiculite, a very hydrated example of a layered silicate. Sometimes you'll also see in the formula of vermiculite, let's say magnesium with some fractional subscript 0.35. These would be exchangeable cations. These are cations exchangeable. These are cations that are not fitting into the octahedral site. So these magnesiums here are in six-fold coordination. These are not. These magnesiums here are fitting in with the water molecules, and they can be pulled in or out of the structure. So vermiculite is a very interesting mineral in that way, in that it can store water. It can also be dehydrated. We can also put some cations in here. It doesn't have to be magnesium. You might be able to squeeze other kinds of materials in and put vermiculite to various kinds of environmental uses. So this is another variation on a theme, and then in another video we'll look at the true micas.